All right. So first practice problem. So you have a kayak travels from the west bank to the east bank of the river with a constant velocity relative to the river, which we'll call VB/R. Okay, and that's going in the I direction. If the river current is constant and flowing in the direction shown, so straight down this direction, determine the velocity of the actual kayak, the time it takes a kayak to cross the river, and the distance it ends up landing downstream. Okay? I want that value of d in terms of your relative velocity, the river velocity, all right, and then plot. And I've actually shown you the plot down below. But let's tackle this problem. Okay? So the first thing you want to notice is, since the river is going straight this way, and he's trying to swim this way with respect to the river, he's going to actually make an angle. Okay, I mean you've seen this before. You don't go straight across. You reach from part from A to C, little distance down from where you start. Okay, so. So what is, how do I start? Let's go right with this. What is this vector form? How do we write that? Is it VB minus VR? Yeah. So let's just write that. So, just again, to remember what the relative velocity means. We have velocity of the kayak or boat with respect to the river is the velocity of the boat minus the velocity of the river. And in here, I now split those up into components that I know. So the velocity of the boat is the velocity of the boat with respect to the river plus the velocity of the river in the I and J components. Okay? You see what I did there? Now, the question becomes, how do we find the time it takes to cross the river? What's that? Nope. It's easier than that. What is the... That's the velocity vector of B, right? What are its components? This is VB with respect to I. And this one is VR. You see how those two are the components of that vector? So, what is the velocity in the x? It's the blue. Oops. And what is the velocity in the y? It's that one. So if I tell you this, to find the time, actually let me use blue. we take our distance, which is big D, and we subtract and we divide by velocity. What's the unit on big D? Meters. This is meters per second. You end up getting seconds. Okay? So really, this is just to look at the components and say, okay, we could do graphical. We split these up into components. We can look at the velocity and the x, divide that by the distance. That'll tell us the time. And then how would we find little d? What's the unit on that? Meters. And then how do we find distance if we have velocity and time? We just multiply them. Then I substituted what my time is. So the biggest thing to always remember in this case is always remember your fundamental relative velocity equation. Okay? And then over here on the left, identify how your vectors are going. So VR is going straight down. VB is the actual vector of the boat or the kayak. And this is what you would actually see, him actually moving this way down towards the bottom of the side or the bottom of the bank. Then here I just split this vector into components, which is your relative and your river velocity. And then you can use those two values to find distance and time. All right, car B turns such that its speed is increased by 0.5 e to the t meters per second squared. If the car starts from rest at 0 degrees, determine the magnitudes of its velocity and acceleration at 2 seconds. All right, give me, what would be some givens? Acceleration. What type of acceleration are you telling me? Okay, so this is actually AT, because the definition of AT is dv dt. So I'm just going to start with that. dv equals AT dt. So dv equals 0.5 e to the t dt. And what is our limits of integration? Well, let's do the left side. Yeah, it starts at rest, right? Yep. Just a v. And the right side, I think it starts at 0. And you could do to t, but we'll leave it as, 2, but we'll leave it as t so we can find an equation. Then we'll just plug in 2. All right? This is v minus, from v to 0. Now what's this integration? Anybody know? The 1/2 comes out front. Integration of e to t becomes e to the t. Yep. Is that what you said? Yep. This is evaluated from 0 to t. So this is v minus 0 equals 1/2 e to the t minus 1/2 e to the 0. What is e to the 0? Anybody know? 1. You see how if you didn't put that in there, you would mess that up? Because technically now the velocity is 1/2 e to the t minus 0.5. At 2 seconds, you plug it in, you get 3.19 meters per second. Was it trying to find velocity? Acceleration. Okay. So what about acceleration? You can? Well, what else do we have to find? Normal. Yeah, so always remember that this is an squared plus at squared. Square root. So an is v squared over rho. So 3.19 squared over 5 meters. 2.04 meters per second squared. And then at, you just plug in 2 seconds. It was 0.5 e to the t at 2 seconds. T is 3.7 meters per second squared. And then finally, you plug it back in, you get 4.22. Okay, for some reason the video got cut off, so I'll finish this review. So here's a train has a speed of 8 meters per second, which is increasing at 0.5 meters per second along this curve. Determine the magnitude of the acceleration of the engine when it reaches point A. 20 seconds. And the radius of curvature there is 400 meters. So the biggest thing you got to remember is that AT is 0.5 meters per second squared. All right, and we integrate that to find our velocity as a function of time. Okay, then we plug in our velocity, which is 18 meters per second, in our AN equation. Okay, to find that the AN is 0.81 meters per second squared. And then finally, we know that the total magnitude of the acceleration is AN squared plus AT squared, and we get 0.95 meters per second squared. Okay? All right, another important equation going around curves is the arc length, S equals R theta, where theta needs to be in radians. Okay? Here is another practice problem. A passenger in an automobile observes that the raindrops make an angle of 30 degrees with a horizontal as the automobile travels forward with a speed of 60 kilometers per hour. Compute the terminal velocity, VR, of the rain if it's assumed to fall vertically. So here, the rain is falling straight down, and we're going to the left. We would see the rain coming at us in this black arrow here. That would be the velocity of the rain with respect to the automobile, because we're sitting in the automobile and here's the angle. So what I do is I said, okay, I know this equation here. Velocity of the rain with respect to the automobile is velocity of the rain minus velocity of the automobile. Rearrange to solve for the velocity of the rain. Now this velocity of the rain equation has two components, the x direction and the y direction. So here, the velocity of the rain in the I equals velocity of the automobile in the I, plus the velocity of the rain with respect to the automobile in the I. Same with the y direction. Okay, we have velocity of the rain velocity of the rain in the j, velocity of the automobile in the j, plus the velocity of the rain with respect to the automobile in the j. And then what I did was I plugged in each value. So let's start with the x direction. There is no velocity of the rain in the x, so that's 0. Velocity of the automobile because I picked my direction to be positive to the right, that would be negative. Then the velocity of the rain with respect to the automobile, cosine the angle, okay, in the I, because I broke up this black vector, okay, and we get velocity of the rain with respect to the automobile to be 69.3. Over here in the y direction, we know that there's a velocity in the j direction. Velocity of the automobile in the j is 0. And we break this black component again, going downward as positive, right here. So now we have the velocity of the rain with respect to the automobile, sine theta in the j, and we plug this value in here to get now velocity of the rain. All right. Now this is using equations graphically. Here's how you would do it. Pick a coordinate system. So let's pick, like we did here, this is positive x, and going down is positive y. So we start with our VR equation, or VR vector, so that goes straight down. So let's do this. So this goes straight down. Then, starting from the same point, we go left, because that's the way the automobile moves, to the left. Okay. Then, because we're on the automobile, we start at this point here, and we go down towards the rain vector. That's our relative velocity vector. And here is our angle. And now we can just use trig to figure out what our velocity of the rain is. Okay.